Hey everyone, welcome to UAV Works, and in this pre-build video we are going to discuss some of the required materials and skills for this project. As this channel is meant to bring more DIY beginners into the FPV and multi-rotor scene, I feel like including an explanation on why one should build this antenna would be beneficial. Before we begin, let me just say that it is absolutely not necessary for you to watch this video to build the actual antenna. If you're an experienced DIYer, go ahead and skip this video to the actual build by clicking the annotation that I will put on the screen. So first things first, we're going to need 10 AUG copper rounds. And notice that this says recommended. The material is recommended because if, say, you don't want to shop online and get 10 AUG copper round, and you have 14 AUG or 16 AUG copper rounds laying around the house, you can go ahead and use that. It's going to be no big deal. So if you don't have that laying around and you want to buy the actual copper round that I use and that I recommend, go ahead and head to eBay, and this link will be in the description. So this is what I use, the 10 feet 10 AUG solid copper grounding wire for the TV or whatever. Very good coaxial, or I'm sorry, not coaxial, but copper wire, and it's very, it's just copper wire, but it's great pricing, free shipping, and you get it pretty fast if you live in the US. This wire does come insulated, so you would need a hobby knife to slice open the insulation. The second thing that we're going to need is 5/8 inch dowels. Now, you might actually need 1/2 inch dowels, but if you are using 10 AUG copper rounds, you don't need the 1/2 inch dowels. This 1/2 inch dowel's purpose is for those who are using more flexible copper rounds to first shape their coil, and when it bounces back or when it expands, one can then transfer it to the 5/8 inch dowels, which is the actual dowel that we're going to use for the build. So where do you get that? Well, any hardware store would do, but technically you can get it at Home Depot. I know that Home Depot is kind of like all around the US, so you should be able to pick this up in the lumber department. Now, the third thing we're going to need is the copper PCB. PCB is short for printed circuit board, by the way, so we need a blank PCB. Again, I bought this off eBay with free shipping. It's $25 for, I think, 9 pieces of 6x6 blank PCB, but if you don't feel like buying 9 pieces at once and paying $25, you can go ahead and just look up, FR4 copper clad double-sided PCBs, and just make sure that dimension is just bigger. The dimension will work out because you're going to be cutting some circles, and well, I guess you could cut squares and just round the edges, but again, that's in the templates, and just go ahead and figure it out. Make sure that whatever you're going to cut is actually going to fit on the PCB, and in my case this will work, and so will the 6x6. So the next thing you're going to need is probably thin wood sheets. Again, this can be picked up at probably Home Depot or your local hardware store if you have a lumber yard. And I would recommend using 1/8 inch wood sheets. I actually bought some Arctic birch ply from my local hobby store, I think, and worked out great for some of my projects. So go ahead and pick some up if you're using the cross support method, which we will also go into a little later. Now, the required skills, just make sure you know how to use a soldering iron. This is actually not a very hard build. Make sure you know how to use a soldering iron and know how to use a power drill or drill press. I would recommend using a drill press, but you could technically do it with a power drill, handheld power drill if you want to. It doesn't really make a difference. Except, of course, drill press is more accurate. So the difficulty, as I said, is pretty easy because this antenna is very wideband, which means it's very forgiving in terms of dimensional tolerances. It just pretty much means that you can have more deviation in your build. Say you don't shape your copper round precisely, it's not going to make that big of a difference. Say like the clover leaf, which has a significantly more or significantly less forgiving dimensional tolerance than the helical. So this is a very good antenna. It's got a few components to solder together. Pretty much you have, let's see, I have this right next to me. You have the helical, which is one part. You have the support, which is the second part. And if you're using the former as the support, this is pretty much, you don't need a cross support. You have the coaxial wire, which is, I guess, the third component for me. And then you have the reflector plate, which is the fourth component. So as you can see, very few components, can be as few as 3 components actually. Very short build time. One of the viewers said that he built this antenna within 15 minutes. So for me, it took about like, I want to say 20 minutes because I machined out my cross and I made sure everything was to dimension. And so again, very short build time, always a plus. And there's no wave trap required for 5.8 gigahertz, which is a great plus because it just pretty much simplifies the build. So at this point, you're probably asking why this antenna if you're a beginner. Well, there are a couple reasons. First of all, it's circularly polarized, which means that it has multipath rejection. And if you don't know what multipath rejection is, that's completely okay. It just pretty much means that when you bank or when your antennas are not completely aligned, you won't get the fuzzy lines. That's as best as I can explain it without getting into the technical details. Pretty much circularly polarized is a good thing. Again, it's easy to make to the desired gain, actually. Well, it's easy to make and it's easy to make to the desired gain, which pretty much I will show you right here. You can actually, where is it? You can make it to 8.5 dBi, 9.5 dBi, or whatever you want. Pretty much it's just adding on more turns actually makes it more directional, which means that you have more, your beam is going to be narrower, but your signal strength, you can receive a stronger signal in the direction that you point it in. That's as best as I can describe it without going into the details. So that's a plus for this antenna. It works incredibly well with the popular cloverleaf antenna, which is, I'm assuming, what you guys are using if you're watching this video. If you don't know what a cloverleaf antenna is, you definitely have to go check it out. I'm going to link a few videos in the description or the annotation, and it's going to teach you guys how to build, or they're going to teach you guys how to build the cloverleaf antennas. There are already a couple videos out there, so I don't know if I should do a build guide on this, but if enough of you guys want to see it, then I guess I'll do it. Okay, again, yep, easy to build, and one of the last things I want to talk about is how the equation can be applied to different frequencies. Now, obviously, not everyone flies on 5.8 gigahertz, so how do you build this for, say, 1.2 gigahertz or 2.4 gigahertz? Well, you go down here on the written guide, which I'm going to have linked in the description below, and you can go down to the cross-insulated helix. If you're using like wood for your support or your whatever, something that's not dielectric. If you're using PVC pipes for your support, then you're going to have to use this set of equations. But most of the time, I think we're going to be dealing with the cross-insulated helix because everyone's probably just going to be lazy and use their wooden dowels as the support. So what you pretty much do is you see the cross width in inches. That's pretty much the diameter of your helical. All you have to do is just take 3,600 divided by the frequency of whatever you're using. So say you're using 1280 megahertz. Then you just do 3,600 divided by 1280, and that's your cross width in inches, or pretty much your diameter. Also, the coil spacing can be found this way. Just do 2,900 divided by the frequency, and pretty much cross length can also be found using the number of turns and multiplied by the coil spacing, which should make intuitive sense. I don't think you guys need to worry about that too much. And the reflector plate size can also be found this way. Now, I read that the reflector plate ideally should be circular, so I guess this measurement right here is going to be the diameter of your reflector plate size. Now, don't worry if you can't get, perfect circle cut out. If you want to just do a square with rounded edges, that's completely fine. Just make sure that the square is bigger than the reflector plate size listed here, I guess. So let's see, what else do we have to cover? Oh, right. For my soldering iron, I'm using the Hako FX888 from Amazon. It's $82, but it's a very, very, very good iron. It's temperature controlled digitally, so pretty much what this means is that you will get very consistent temperature on your soldering iron. It's 70 watts, but when it senses that the temperature is dropping on the iron tip, it'll apply more power, I guess, and it will heat up. So right here it says that it maintains idle temperature within 1.8 degrees Fahrenheit or 1 degree Celsius, which is incredibly helpful when you're doing soldering jobs and just makes your joints better. So go ahead, and if you have the means to, just get this soldering iron. It's very, very good. And so if you found this video helpful, I would greatly appreciate it if you can click the thumbs up button below or share my guides with your friends. Just a small update on the tricopter electronics setup video, by the way. I'm working very hard on it. Trust me, it has not been forgotten. To stay up to date with more of my tutorials, feel free to hit the subscribe button or click the annotation on the screen. Thank you very much for watching, and I hope to see you again in the build.